Hi friends, in this lecture we'll discuss about some of the variants of Turing machines. Turing machines which we have discussed in our previous sessions are all single tape Turing machines. Today we'll discuss two new models of Turing machines. First one, multi-tape Turing machine, a Turing machine which has more than one tape. Second, non-deterministic Turing machine, a machine in which for a given delta transition q comma a, it may go to multiple states with more than one transitions. As stated, multi-tape Turing machine contains more than one tape. In this example, the finite control is connected to tape 1, second tape, so on up to k tapes through the read-write head. Each tape is divided into cell. First tape holds the input string. Rest all tapes contain blank symbol initially. The first tape read-write head will be pointing to the leftmost input symbol of the given string. A multi-tape Turing machine has Q, a finite set of states, Q0, an initial state, F, which is a subset of Q called the set of final states, P, a set of tape symbols, B, blank symbol which is not present in P, and assume that summation is a subset of tau and blank does not belong to summation. And delta is a partial function from q into tau raised to k into q into tau raised to k into L R or S whole raised to k. And the move depends upon the current state and k tape symbols under k tape heads. In a typical move, M enters a new state. On each tape, a new symbol is written in the cell under the head. Each tape head moves to the left or right or stays in the same cell. The heads move independently, so some move to the left, some to the right, and remaining heads do not move. The initial ID has the initial state Q0, input string W in the input tape, and empty string of blanks in the remaining k-1 tapes. And an accepting ID has a final state and some strings in each of the k tapes. Let us see a simple example for multi-tape Turing machine consisting of two tapes, tape 1 and tape 2. At some instance, Q0 is pointing at A in tape 1 and F in tape 2. And if we have a transition from Q0 AF where the state changes from Q0 to Q1, A is replaced as X. So you can see here A is replaced as X. F is replaced as Y. So F is replaced as Y. Then tape 1 will move towards the right. So previously it was pointing to A. Now A is replaced as X and it is moved towards the right pointing to B. And tape 2 will be moved towards, read-write head will be moved towards the left. So previously it was pointing to F. F is replaced as Y and it is moved towards the left and it is at present pointing to E. Let us see a theorem which states that every language accepted by a multi-tape Turing machine is acceptable by some single-tape Turing machine, also called as standard Turing machine. To prove, suppose a language is accepted by a k-tape Turing machine M. We simulate M with a single-tape Turing machine with 2k tracks, in which the second, fourth, so on up to 2kth tracks hold the contents of the k-tapes, and first, third, so on up to 2k minus 1th tracks hold a head marker X to indicate the position of the respective tape head. Let us see how we can simulate multi-tape Turing machine into single-tape Turing machine. So here we have a two-tape Turing machine which is simulated into a single-tape Turing machine with 4 tracks, where tape 1 content is stored in second track, tape 2 content is stored in fourth track. Since symbol A and F are the current symbols to be scanned, so the head marker X is on A in first track and head marker X is pointing to F in the third track. To simulate a move of M, the 2K track Turing machine M1 must visit the two head markers and store the scanned symbols in its control. Keeping track of head markers visited and those to be visited is achieved by keeping a count and storing it in finite control of M1. The finite control of M1 has also the information about the states of M and its moves. After visiting both the head markers, M1 knows the tape symbols being scanned by the two heads of M. Let us see a move in a multi-tape Turing machine simulated in a single-tape Turing machine with multiple tracks. Given the current state at Q0, both the heads pointing at A and F, if we have the current move, then Q0 is changed to Q1, A is replaced as X, F is replaced as Y. First tape, that is second track content, read write head will move towards the right. So previously it was on A is replaced as X and it is moved towards the right. And the second tape content F is replaced as Y and the head will move towards the left. So F is replaced as Y. Head was at this position. Now it is moved towards the left. So this is a simple example how a move is made in single tape Turing machine with multiple tracks. Discussed in the previous example, M1 revisits each of the head markers. it changes the tape symbols in the corresponding track of M1 based on the information regarding the move of M corresponding to the state and the tape symbol in the corresponding tape M. It moves the header markers to the left or right, and M1 changes the state of M in its control. So this is the simulation of a single move of M. So at the end of this, M1 is ready to implement its next move based on the revised positions of its head markers and the changed state available in its control. M1 accepts a string W if the new state of M as recorded in its control at the end of the processing of string is a final state of M. Let us see a few more definitions of multi-tape Turing machine. Let M be a Turing machine and W an input string. The running time of M on input W is the number of steps that M takes before halting. If M does not halt on an input string W, then the running time of M on W is infinite. Note that some Turing machines may not halt on all inputs of length n, but we are interested in computing the running time only when the Turing machine halts. So the time complexity of a Turing machine M in the function T of n being the input size, where T of n is defined as the maximum of the running time of M over all inputs W of size n. So let us see one more theorem on multi-tape Turing machine, which states that if M1 is the single tape Turing machine simulating multi-tape Turing machine M, then the time taken by M1 to simulate n moves of M is big O of n square. So to prove, let M be a k-tape Turing machine. After M moves of M, the head markers of M1 will be separated by 2n cells or even less. So to simulate a move of M, the Turing machine M1 must visit all the k head markers. If M starts with the leftmost head marker, M1 will go through all the head markers by moving right by at most 2n cells. To simulate the change in each tape, M1 must move at most 2n cells. To simulate changes in k tapes, it requires at most 2 moves in the reverse direction for each tape. Thus, the total number of moves by M1 for simulating one move is at most 4n plus 2k. For n moves, it will be n into 4n plus 2k. As the constant k is independent of n, the time taken by M1 is big O of n square. So this is how multi-tape Turing machine works. Let us discuss another variant of Turing machine known as non-deterministic Turing machine, which consists of 7 tuples, namely Q summation tau delta Q naught BF, where Q is a finite non-empty set of states, tau is a finite non-empty set of tape symbols, B belongs to tau, which is a blank symbol, summation is a non-empty set of input symbols, is a subset of tau, and blank does not belong to summation. Delta is a partial function from Q into tau and is a power set of Q into tau into left or right move. Q0 belongs to Q, which is the initial state, and F is a subset of Q, which is the set of final states. Let us see a theorem which states that if M is a non-deterministic Turing machine, there is a deterministic Turing machine M1 such that T of M is equals to T of M1. To prove, we must construct M1 as a multi-tape Turing machine. Each symbol in the input string leads to a change in ID. M1 should be able to reach all IDs and stop when an ID containing a final state is reached. So the first step is used to store the IDs of M as a sequence and the state of M. These IDs are separated by a symbol star. The current ID is known by marking an X along with the ID separator star. All the IDs to the left of the current one has been explored already and so can be ignored subsequently. Note that the current ID is decided by the current input symbol of W. To process the current ID, M1 performs first. M1 examines the current state and the scanned symbol of the current ID. Using the knowledge of moves of M stored in the finite control of M1, it checks whether the state in the current ID is an accepting state. In this case, M1 accepts and stops simulating M. In the next step, if the state Q, say in the current ID XQAY, is not an accepting state of M and delta of QA has K triples, M1 copies the ID XQAY in second tape and makes K copies of this ID at the end of the sequence of IDs in tape 2. Then M1 modifies these K IDs in tape 2 according to K choices given by delta of Q, A. M1 returns to the marked current ID, erases the mark X and marks the next ID separator star with X. Then M1 goes back to step 1. So this is how non-deterministic Turing machine works. We discussed two variants of Turing machine. First, multi-tape Turing machine and second, non-deterministic Turing machine. Thank you.